is our AP Chemistry lesson video for Chapter 17. This is Part 3, and I'm going to cover Section 17.4 and 17.5. So hopefully if you made it through Part 2, you are ready to continue. I will go ahead and tell you, now we're at KSP. KSP is much easier than doing full titrations. Okay, so just bear with me. We're going to make it through it. It's going to be fine. You made it through the hardest part, and that was Section 17.3. All right, assuming you actually made it through that video. So, the solubility product constant is written like an equilibrium constant. Remember, pure liquids and solids are not listed. So when we're talking about solubility, we're talking about a solid dissolving in water to break up into its ions. So our K value, of course, is products over reactants, just as it always is. But the reason you only see products is our products are aqueous, our reactant is solid. So remember, we don't include liquids and solids. Now, it's been a while since we've had to use coefficients because we've been on acids and bases. But for example, if there had been a 2 here, I would have squared that one. Okay, so just don't forget about that. So if they ask you to write KSP for a substance, you just break it up into ions and then just write the ions as the product of them as your K value. So it says, write the expression for the solubility product constant for CaF2. Now, once you get good at these, you won't need to sit there and necessarily write the reaction, but I'm going to write the reaction just so you get used to seeing it. Okay, so we have our solid, and it's going to break up into calcium with a positive 2 and 2 fluorines or fluoride ions with a negative 1. Okay, so you got to be careful of that. You have to actually write how many ions you're going to get. So when I write my KSP, it is products, so I'm going to do the concentration of calcium ion times the concentration of fluoride ion, but I'm going to square it because of the 2, remember. And then I'm not going to divide by CaF2 because that's a solid. We don't put it in there. Okay, so that would be my expression. So see how we're going back to super easy. I mean, ice charts are coming, don't get me wrong, but bar charts aren't. Like the bar charts are the long ones. Okay, so y'all try these two. I'll assume you paused it and tried it, and we'll look at it together. So it says, give the solubility product constant expression for barium carbonate. Okay, so barium carbonate is this right here. It's going to be a solid. It's going to break into its ions. So when I write my KSP, I just do products, which is the barium ion and the carbonate ion, over reactants, but I don't need to because it's a pure solid. Remember, pure solids and liquids like water don't go in your K value or K expression. Alright, so I'll assume you've tried the bottom one. It says silver 1 sulfate. So the important thing to remember is you do need to balance your charges still. So silver 1 means it has a positive 1 charge. Sulfate, on the other hand, has a negative 2 charge. So I actually need 2 silvers to make this. Alright, that's going to be my solid, so I'm going to get 2 silver ions and a sulfate ion. Okay, so see, if you forget to balance your charges, you might end up missing one of these. And this should be like a super simple one if it's on the AP exam. Okay, so it's products, so I do my silver ion, but of course, ooh, that was a crazy looking bracket. But of course, I'm going to square it because of the 2, and my sulfate ion, and then I'll leave off the reactant because of course it's a pure solid. Okay, so now that we know how to write the KSP expressions, let's learn how to plug into them and solve for stuff. So molar solubility is the number of moles of the solute that dissolve in forming a liter of saturated solution of the solute. Okay, so we're talking about how much will dissolve to make a saturated liter of solution. The KSP is the equilibrium constant between the ionic solid and its aqueous ions. Okay, so we have the solid versus when it breaks apart. So let's look at our first one. This question is super duper long, but don't worry, the work is not. I only spent this much room working on it. Alright, so it says solid silver chromate is added to pure water at 25 degrees Celsius. Some of the solid remains undissolved at the bottom of the flask. The mixture is stirred for several days to ensure that equilibrium is achieved between the undissolved silver chromate and the solution. Analysis of the equilibrated solution shows that its silver ion concentration is 1.3 times 10 to the negative 4 molar. Okay, this question continues on the next slide, so I'm almost positive I will need this. Okay, so silver ion concentration at equilibrium is 1.3 times 10 to the negative 4 molar. So let me go ahead and write that down. So my silver ion concentration at equilibrium is, what did I say? 1.3 times 10 to the negative 4 molar. All right, continuing the question. Assuming that the silver chromate dissociates completely in water and that there are no other important equilibria involving silver or chromate ions, that's called common ion effect. We've talked about it before, but we'll talk about it again in a little bit. In the solution, calculate KSP for this compound. Okay, so I need to calculate my KSP. So first I got to set up an ice chart because I need to get my equilibrium values for everything. So we have our Ag2CrO4 solid splitting up into 2 Ag positive and a chromate ion. All right, so let's set up our ice chart. Because this is a solid, we don't care about it. Okay, in the beginning, it did not say we started with any of our ions. Okay, so in the beginning, we started with 0, but it told me at equilibrium, my silver ion concentration was 1.3 times 10 to the negative 4 molar. And these ice charts are so easy to fill out. A lot of times, you'll get to where you can start doing these in your head. Okay, but the thing is, if I was adding, like, let me just put it here real quick. I would add 2x for this, but I would only add x for this one because this has a 2. So I added 1.3 times 10 to the negative 4 here to get this. So that means I'm only going to add half of that to the chromate because for every 2 silver ions, I'll only get 1 chromate ion. So half of 1.3 times 10 to the 4 is 6.5 times 10 to the negative 5. And see, you could have done that in your mind. You could have been like, oh, okay, I got the silver, this is going to be half of that. Like, you probably could have done that in your head. Okay, so now we know that KSP, just because we haven't learned how to write these for a while, I'm going to actually write the expression, is just my products, which is Ag positive, but I'm going to square it over my reactants. But I don't need to put reactants because it's just a solid. So then I just plug in. So KSP equals my silver ion concentration, which is 1.3 times 10 to the negative 4. I'm going to drop those units just because K has no units, times my chromate. And don't forget to square it. Again, since we've been doing titrations and pretty much everything was 1 to 1, we haven't had to use like the plus 2x or squaring anything for a while. And so once I solve, KSP ends up being 1.05 times 10 to the negative 12. Just like that. Alright, so that's all you have to do to solve for your K value. So see, that's so much easier than calculating pH at equivalence point for a strong, weak titration. Alright, so y'all try the next one. I'll assume you read this super long question and that you went ahead and tried it. Whew, I did not give myself a lot of room to work. Let me see what the next slide looks like. Don't look at the answer now. Ooh, okay. I might go back to the previous one to work out. Well, I can just erase as I go. Alright, so it says a saturated solution of magnesium hydroxide in contact with undissolved solid is prepared at 25 degrees Celsius. The pH of the solution is found to be 10.17. So remember, I told you, whenever they give you pH, we assume that is at equilibrium. Assuming that magnesium hydroxide dissociates completely in water and that there are no other simultaneous equilibria involving magnesium or hydroxide ions, so in other words, no common ion effect, in the solution, calculate KSP for this compound. So, what I know is I have magnesium hydroxide dissolving in water. So I have MgOH2 solid, and it's going to break up into the Mg positive 2 ion and 2 of the hydroxide ions. Okay, so I set up my ice chart. So I don't care about any of the solid. Initially, I'm not going to start with anything because it told me there are no other simultaneous equilibria involved. So I don't have an equilibrium amount, but I can get it. For pH, you can always get to H plus or OH minus. What would help us in this one is to get OH minus. All right, so for that one, I said, all right, well, POH is 14 minus 10.17, and I got 3.83. And then I said OH minus, this was just me using pH square formulas, is 10 to the negative 3.83, which gives me 1.48 times 10 to the negative 4 molar. And this is for OH minus, and this is at equilibrium. So that means down here, this would be 1.48 times 10 to the negative 4 molar. that means I added that much. But the thing is, this is not 1 to 1. This is 2 to 1. So that means I'm only going to add half as much to the magnesium, because for every 1 magnesium, I'm going to get 2 OHs. So half of the 1.48 times 10 to the negative 4 is 7.4 times 10 to the negative 5. So you just got to be careful of that stoichiometry. All right, so now we're ready to plug in. So KSP equals, this is the last time I'm going to write the formula out again. Okay, and then we'll move past to where I think you can do it on your own. All right, so we have Mg with a positive 2. We have OH minus, but because that has a coefficient of 2, I'm going to square it. And so then I just plug in. So my magnesium ion concentration, 7.4 times 10 to the negative 5. I'm going to drop units because K has no units. And my hydroxide is 1.48 times 10 to the negative 4, and I'm going to square that. And once I solved, I ended up getting 1.62 times 10 to the negative 12. Okay, so if they ever give you pH, just remember, or POH, you can always get H plus or OH minus. The reason I went for OH minus was because no H plus is in this reaction, so it wouldn't be helpful to calculate that. All right, so hopefully you got that one right. All right, so let's keep on moving. All right, so let's look at our next one together. So this is still very similar, it's just changing up units on us. So it says the KSP for CaF2 is 3.9 times 10 to the negative 11 at 25 degrees Celsius. Okay, so this time they gave me KSP. Assuming that calcium fluoride dissociates completely upon dissolving and that there are no other important equilibria, so no common ion, affecting its solubility, calculate the solubility of CaF2 in grams per liter. So in other words, we're not trying to calculate the molarity of CaF2. We want our answer in grams per liter, not moles per liter. All right, so we set up our ice chart, of course. So we have CaF2 solid. And like I said, once you get good at these, you probably won't have to set up an ice chart for all of them. You can kind of start doing it in your head. But if you never get to that point, that's not a big deal. All right, so we don't care about CaF2 because it's a solid. All right, they told me I'm not starting with either product. So I'm going to do plus x. For this one, I'm going to do plus 2x because of that coefficient. So this will be x and 2x. Now this is where you have to be careful. So actually I am going to go ahead and write the KSP expression for you again. So KSP is products, so my calcium ion and my fluoride ion, but I'm going to square it over reactants, which is a solid, so it doesn't matter. So then I just plug in. So my KSP is 3.9 times 10 to the negative 11 equals, my calcium is x. My fluorine is 2x squared. Okay, this is why I say you gotta be careful. Okay, because you're gonna square the 2 and the x. So what it ends up being is 4x cubed. Okay, because see, we'll square the 2, so that's 4. And then this is x squared, but you have times another x. So it becomes 4x cubed. So once I solve for x, I end up getting, whoops, I lost my place. Oh, I found my place. 2.14 times 10 to the negative 4 molar. And that's going to be for my Ca positive 2, which is going to be for my CaF2 because it's 1 to 1. One CaF2 makes one Ca. All right, but the problem is it didn't ask me for molarity. It asked me for grams per liter. Okay, so I know that 2.14 times 10 to the negative 4 is moles per liter of CaF2. So I just need to convert moles to grams. So 1 mole of CaF2 is, I just use the molar mass, 78 grams. So my moles cancel, and so then I ended up getting 0.017 grams of CaF2 per liter of solution. Just like that. Okay, so all I did, just to recap, was I set up my ice chart, I put my K value, I solved for X, that gave me molarity, which a lot of times they'll just ask for that. They'll just say, what's the molarity? And then you could have stopped here, but because they asked for grams per liter, I had to change my moles to grams, just like that. All right, so y'all can obviously try the next one. And so just be careful of those coefficients, because again, we haven't been working with coefficients here for a little bit. All right, so you try this one. I'll assume you've done that, and we'll look at it together. All right, so it says the KSP for LaF3 is 2 times 10 to the negative 19. What is the solubility of LaF3 in water in moles per liter? So notice this time I can just get to molarity and I'm okay. I don't have to do the grams per liter thing. All right, so I set up my ice chart. And so be careful, you're going to get 1 La, but you're going to get 3 F minus this time. Okay, because see, we're going to get 3 of them. So solid doesn't matter. It didn't tell me I'm starting with either of my products, so I'm going to do plus X. For this one, I'm going to do plus 3X because of that coefficient. So it's X and then 3X. All right, so I set up my KSP value, and so again, I'm going to actually write it out just because I don't want y'all to miss any of like the powers or anything like that. So we have our concentration of La times our concentration of F minus, but it's going to be cubed. All right, so then I plug in. So my K value is 2 times 10 to the negative 19. My La is just X. My F minus is 3X, but I'm going to cube that. So be aware, you're going to cube the 3 and cube the X. Okay, so it ends up being 3 cubed is 3 times 3 times 3, which is of course 27. All right, and then I have X cubed, but times another X, so X to the 4th. So once I solve for X, I end up getting 9.28 times 10 to the negative 6 molar, and that is for La, but that is also for LaF3. Okay, and so since it asks for molarity, that's what I'm looking for. Okay, so see, you have to be careful because if they asked about F, you know, that's 3X, whereas La is just X. Alright, and so make sure you know how to do like roots that aren't just square roots, okay? Like if you needed to do like cube root or anything like that, make sure you know how to do that in your calculator. If you're in my class, obviously if you don't, just show me your calculator and I'll show you how to do it. But otherwise you might have to Google it. Alright, and I got to stick with molarity for that one because of course it only asks for molarity. Alright, so section 17.5. See how much faster this is moving than 17.3? Alright, so what will affect the solubility? Like how can I either increase or decrease how soluble something is? So the solubility of a substance is affected by temperature as well as by the presence of other solutes. So one thing I want to go back and point out, not on this one, is here. It says the KSP is this at 25 degrees Celsius. That means that K values change with temperature, as we've discussed all the way back since chapter 15. Okay, K values change with temperature. 3 other factors that affect solubility are the presence of common ions. Now we've talked briefly about this, so we're going to talk about it more. The pH of the solution, and the presence of complexing agents. So let's talk common ion first. So it's called common ion effect. So in general, the solubility of a slightly soluble salt is decreased by the presence of a second solute that furnishes the common ion. So like if I'm trying to dissolve CaF2, but I already have some F in there, that's going to decrease solubility. So think about Le Chatelier's principle, because of course if you increase one of the products concentrations, it's going to shift to the reactants. So it says calculate the molar solubility of CaF2 at 25 degrees Celsius in a solution that is 0.01 molar CaNO3. So first thing I have to do is notice this is the common ion. Okay, NO3 is not in CaF2, so it doesn't affect it at all. Alright, and it gives me the KSP right here. So I write my reaction, so CaF2 splitting up into Ca positive 2 and 2F minus. Alright, I'm going to start dropping the solid and aqueous. Okay, if you see ionic charges, you know it's aqueous. Alright, we are not interested in the solid. It tells me that I'm actually starting with 0.01 molar calcium because that's already in there. It does not tell me I'm starting with any of the fluoride ion though. So I'm going to add X and add 2X. Remember, don't forget that coefficient. So I get 0.01 plus X, and I get 2X for here. Alright, so I'll look up here. This is less than 10 to the negative 5, or like I said, most of the time on the AP exam, 10 to the negative 4 is small enough. So I can do my assumption. So my assumption is I can get rid of this. All right, so then I set up my K value. So KSP is my calcium ion concentration times my fluoride ion concentration, but squared because of that. I don't have to divide by my reactants because, of course, it's a solid. So then I just plug in. So my KSP is 3.9 times 10 to the negative 11. My calcium is 0.01. And my fluorine is 2x squared. So remember, don't forget that's really 4x squared. So once I solve for x, I ended up getting 3.12 times 10 to the negative 5 molar. So that is the molar solubility. That's how many moles per liter will dissolve if I have that much calcium already. All right, so now let's look at the next one. So the next one, we have a solution that's 0.01 molar NaF. Well, Na is not a common ion, F is. So I have some fluoride ions to start with. So I set up my reaction again. So CaF2 is going to break into Ca positive 2, F negative, but there's two of them. Set up my ice chart. Remember, solids don't matter. This time I'm starting with no calcium, but I'm starting with 0.01 molar for my fluorine. All right, so I'm going to add my X and add my 2X here. Okay, don't forget about that coefficient. Like I said, we do acids and bases so long, and it's usually almost always 1 to 1 that it's like you forget to do that kind of stuff. All right, so we end up getting that this is X, this is 0.01 plus 2X. However, again, my K value is small enough to assume, so I can get rid of this 2x. So then I just set it up. So over here, I've already written what KSP is. KSP has the same expression, so let me just go ahead and plug in. So I do my 3.9 times 10 to the negative 11 equals my Ca, which is x, times my 0.01, but don't forget, you got to square it. Okay, you've got to remember to square it. All right, so once I solve for x equals 3.9 times 10 to the negative 7 molar. So that would be the molar solubility if I start with that much F. And so notice the molar solubilities are different. This is 10 to the negative 5 and this is 10 to the negative 7 because the ions aren't 1-to-1 ratio. So they have different effects on the overall KSP. Well, not on the KSP, but on the molar solubility. KSP remains the same because we're at the same temperature. Alright, so let me let you try one or two. Maybe you'll get lucky and have an A and B also. And here I just put moles per liter, but molarity is fine. Alright, so you try this one. I'll assume you've done it already, and then we'll look at it together. Alright, so it says the value for KSP for manganese 2 hydroxide is 1.6 times 10 to the negative 13. Calculate the molar solubility of manganese hydroxide in a solution that contains 0.02 molar NaOH. So obviously they don't have Na in common, they have OH in common. All right, so I'm starting with some hydroxide already. So let me start with my formula, or my equation. So we have our manganese hydroxide breaking up into manganese and 2 hydroxides. So remember, for ice charts, we're not interested in solids. It didn't tell me I'm starting with any manganese, but it did tell me I'm starting with 0.02 molar of my hydroxide. So then I add x, I add 2x, and I get x and 0.02 plus 2x. But if I look, my K value is definitely small enough to assume. So I can get rid of that 2x. So what I end up having is my KSP is my concentration of Mn ions times concentration of hydroxide, but I'm going to square it because of that 2. So you do the 2x and you square it. And so then I plug in. So my KSP is 1.6 times 10 to the negative 13. My manganese is just x, and my hydroxide is 0.02, but I'm going to square that. Okay, and so then once I solve for x, let's see, where am I? Whoops, need to turn the page. Once I solve for x, I got 4 times 10 to the negative 10 molar. Just like that. All right, so hopefully you got that one right. So see how much easier it is than titrations? We just had to get through titrations. Who knew adding an acid and a base together could be so difficult, especially with one sweet? All right, so now let's talk about pH. Okay, so we just did common ion effects. So solubility decreases if we have a common ion present because, of course, that shifts our equilibrium towards the reactants, so less will dissolve. So now let's talk about pH. The pH of a solution will affect the solubility of any substance whose anion is basic. In general, if a compound contains a basic anion, the anion of a weak acid, not a strong acid, its solubility will increase as the solution becomes more acidic. Okay, so if we look and there's an anion from a weak acid, then its solubility will increase if we add H+, because then it can react with that conjugate base. So, oh, that picture is so horrible, even up close. I'm just going to skip it. I obviously could not find a better quality picture. All right, so let's look at this one together. So it says, which of the following substances will be more soluble in acidic solution that contains than in a basic solution? Anytime something has OH-, if you add H+, they will react to form water, okay, which would in turn reduce the concentration of OH-, so this would be more soluble. Okay, so just whenever you have H+ and OH- together, they are going to neutralize and make water every time. All right, so now let's look at part B, C, and D. So CO3 is not from a strong acid, it's from a weak acid. It comes from carbonic acid originally, but then it would be HCO3 negative to make this, but either way, it's not a strong acid. This comes from a weak acid, so yes, it would also be more soluble. F comes from HF, which is also a weak acid. So yes, it would be more soluble. Because what's going to happen is, like, let's just look at the F one. The same thing happens for the CO3. If you have F- and you make it more acidic, you add H+, then what's going to happen is you're going to make the HF, and that will reduce the F-. And if you reduce the product, it will shift to the products. Now AgCl, Cl is from a strong acid. So remember, strong acids, their conjugate bases are of negligible basic value. So there is no change for this one. Or what did I write? Oh, yep, I just wrote no change. All right. No change for is it more soluble and acidic or basic. It wouldn't matter either way. All right, so hopefully that wasn't too bad. That kind of goes back to salts being acidic, basic, or neutral type scenario that we've talked about before. All right, so last thing we got to talk about is complex ions. But guess what? We do not have to do complex ions. Yay! Oh, I'm just kidding. We do. Just kidding. We don't. Or do we? Just kidding. We really don't. We don't have to do complex ions. So last thing we got to talk about is amphoterism. Amphoteric oxides and hydroxides can act as acids or bases. Amphoteric is a substance that can be made to dissolve in either acidic or basic solutions. Amphiprotic is a particle that can act as an acid or base by losing or gaining a proton. Okay, so amphiprotic, the substance itself is acting as an acid or base by losing or gaining a proton, whereas amphoteric, we can make it dissolve in either acidic or basic solutions. So they're related. Amphoteric species dissolve in acidic solutions because they contain basic anions. However, they can also dissolve in basic solutions because they can form complex ions. But remember, we don't have to cover complex ions, so we don't really need to go into that anymore. Alright, so hopefully that video wasn't nearly as bad as the part 2 where we did section 17.3. And y'all, the best news is there's only one more after this. There will be a part 4 and then we are done with equilibrium.